Okay, so I think the first videotape needs to take a look at Newton's three laws, but from a conceptual standpoint. Because I think if you don't have a handle on the conceptual nature of this, then you're really not going to be able to solve these problems and do anything with any real meaning to them. So while I know you think you may know this, let's make sure we're all on the same page. So there are three laws. Newton's first law. You know this better as the law of inertia. Let's talk a little bit about what it is and what it is not. First and foremost, inertia, the tendency of an object to stay at rest or to stay in motion. Let's remove it from the planet and put it in space. If you've got an elephant, it's harder to get moving in space, and if it's moving in space, it's harder to slow down than, say, a mouse. Why? Most everybody would say because of its weight, because that's what we're used to on Earth's atmosphere, or on Earth. We have a pull of gravity that's downward. But the real reality of it is its mass. And if you've got an elephant floating in space, and we assume there's no other gravitational bodies around it, then it has no weight. So think of inertia as associated with mass. The larger the mass, the larger inertia that it has. Newton's first law basically says this. It's what everybody likes to quote. Something is going to stay in a straight line, in constant motion, or uniform motion, right? Until acted on by some unbalanced force. So something's moving at a constant speed, or something that's at rest. Both of those are considered uniform motion. The difference between the two, if something's at rest, let's start with the one that everybody knows. That means the net force is zero. So let's just say for granted, it's a box on the table. It's the weight pulling downward, and it's the normal force upwards. And by the way, on your formula booklets and by the IB, they oftentimes refer to the normal force as the capital letter R, so just get used to it. If something is in static equilibrium, sorry about the E, then that means the net force is zero. That means up is equal to down. There's nobody winning the tug of war, and this thing will remain there as long as those forces are balanced, right? Granted, it's not moving, but it's in an equilibrium. Law of inertia said that's going to continue to be true unless there's an unbalanced force, right? The other possibility for this is something that's, say, sliding along, right? And let's say it's sliding along ice, right? And it's moving at a constant speed. These are key words. If it's at a constant speed, that again means, and I'm going to write it for everything, that means that the sum of the forces are zero. The net force is zero. There is nobody winning the tug of war. So if something is traveling at a constant speed, that means if somebody's pushing it or pulling it, let's say, with some kind of force, there better be some other force in the opposite direction. If it's sliding across ice, we'll say that it's the force of friction. Those two forces must be equal to one another if this thing is traveling at a constant speed. This is known as dynamic equilibrium, right? Another form of equilibrium, sorry guys, equilibrium, okay? In both cases, the net force is zero. These are key things that you look for. And what Newton's first law says, look, this guy is going to keep moving along as long as those forces are balanced until something becomes unbalanced. Then something's going to change. Something that's already moving is going to continue to want to keep moving unless it's acted on by a force. That elephant floating in space, if you give it a push, it's going to keep going on forever, right? It's going to just keep going on forever. The way that Galileo looked at this is he said, okay, if I have a bowl, right, and I release a ball from up here, and assuming that no energy is lost, this bowl will roll down and it'll roll back up to the exact same height that it was started from. Then he envisioned the bowl such that it was more like that. And he says, okay, if I release that ball from that height, it's still going to seek that same level, right? It's going to go up to the same height. It's going to travel farther because the bowl is less steep on this side. He finally reasoned, okay, what if I have a bowl where the other side of it goes up over at infinity? That means if I release this ball and no energy is lost, this thing will just keep rolling along, seeking that same level that it was released from. So that means this guy's going to keep moving along at a constant speed. It's going to be in dynamic equilibrium. And what Newton's first law says is, hey, it's going to continue traveling at that constant speed until some other force comes along that either speeds it up, slows it down, changes its direction, does something. Right? That's the gist of Newton's first law. What I need you to understand is this. Inertia is not a force. Never, ever, ever do I want to see it on a force diagram. There's no such thing as the force of inertia, right? If you're desperately looking on a force diagram to talk about what the force is and you can't name it, there's a really good chance that there is no force there. Okay? So far, so good. So inertia is not a force. It's just associated with mass. But since we talk about Newton's first law, I think people tend to screw it up and make it a force. All right, let's go to your favorite one, Newton's second law. Newton's second law talks about that unbalanced force that first law mentioned. So life's happy, things are in dynamic or in static equilibrium, the net force is zero, right? Then when that outside or unbalanced force acts upon it, something happens. So what Newton's second law said was this. And first let's write it the way that Newton wrote it. And then we'll kind of decompose it, because you have a little bit of insight now. When Newton first wrote this, he wrote it like so. And basically what he says is, look, if you change the momentum, and remember, just from previous, momentum is mass times velocity. If you change the momentum over a period of time, there's a force. Now I want you to think about this, right? If you kick a soccer ball, you've changed its momentum. It's gone from zero to some velocity. It's got mass, so now it has momentum. Why? Because you applied a net force to it. Newton had some insight because he said, look, you could change the velocity, you could also change the mass. This is kind of what happens when we launch a rocket into space. As we burn the fuel on it, right, we change the mass of it, that also changed the momentum as well. Now this is not the normal form that you guys think of Newton's second law. You actually, and I'm going to write it over here and I'm getting ahead because we're going to do another video of this later, but you tend to call this impulse, and that's what you associate it with, right? Change in momentum is the impulse. This is what you dealt with when you talked about punching somebody. If they roll with a punch, they extend the time, you feel less force. This is how an airbag works, right? Your face is traveling 60 miles per hour when you smash into a wall. The airbag deploys. Your face takes longer time to slow down to rest, so the force is less. You know this is impulse. But it comes from Newton's second law, right? That's the origin of it. Let me derive this in a manner that's something you're used to seeing. If I rewrite this, I know that momentum, change in momentum, is the final momentum minus the initial momentum, right? Over time. Well, I know momentum is mass times velocity. So it's going to be mass times the final velocity, right? Minus mass times the initial velocity, right? Divided by delta t. If I factor out a mass, I get final velocity minus initial velocity over time. Well, if I change the velocity, let me put vectors over here, these guys, sorry. If I change the velocity per unit time, you know this better is, yeah, you got it, acceleration. And that's how you know Newton's second law. You know it as F is equal to ma, right? That's where it comes from. But this is how it was originally written, as the rate of change of the momentum. Newton had some foresight thinking, okay, it could encompass many more things. Let me just kind of go one step further. What Newton's second law says really is this. It says the acceleration of an object is directly proportional, and I'm going to put a net here, to the net force acting on it, and it's inversely proportional to the mass. Here's the way I like to write it in Sesame Street terms, right? You're going to have a big acceleration, right? If you have a big force, net force, acting on a mass, right? The bigger this force, the bigger the acceleration. The other thing I want you to notice is that these guys are vector, right? This acceleration is always in the same direction as the force, the net force, always, right? So if you have a tug of war going on a block, right? And I've got two forces on this side, and I've got one force on this side. These two guys together are going to beat this one. Well, which way is the block going to accelerate? In the direction of the net force. So that's what those vectors are very important for. The other thing that it says is, hey, look, my acceleration is going to be small if for the same net force I have a really big mass. Well, that makes sense, right? It's harder to accelerate an elephant than it is to accelerate, say, I don't know, a rock, right? Whether it's in space or whether it's here on Earth. Bottom line is, this is what Newton's second law is. The most important thing that I want you to get from this conceptual stuff is kind of this idea of big, small, that these guys are in the same direction. But it's this, and this is critical. This law is a one-body law. That's important. What do I mean by one body? You draw all the forces on a single object. When you use Newton's second law, you're looking at all the forces acting on one object. If there are more objects, then you have to make a force diagram and apply Newton's second law to them independently. Now this is really important because the third law, the one that most people screw up, is not this. So I'm going to make a real big distinction between these two guys. So Newton's second law is a one-body law. Okay? And again, it's your old friend, F is equal to ma. F is the net force. F is the net force. Who's winning the tug of war and by how much? The third law is the law that I hate the way people name it. Newton's third law. It's often referred to as action, reaction law, right? And everybody knows the definition. For every action, there's an equal and opposite reaction. I hate that. I literally hate that because people really have no clue what that means. And they use it wrong all the time. I'm going to show you how we use this, but before I go into anything else, I want to make that distinction between this and the second law. Newton's third law is a two-body law. In other words, every time we talk about Newton's third law, we have to talk about two things. There are two things always going to be involved, right? So the example that I use, and please pardon my art, everyone, you're just going to have to get over your bad self, right? So here I am, here's my eye, here's my nose, here's my mouth, right? And somebody's going to touch me. So here's somebody's finger on their big hand, right? They're touching my forehead. The way that you need to think about Newton's third law is this. I cannot be touched without me touching the person who's touching me. Say that one more time. I cannot be touched without me also touching the person who's touching me. Notice I mentioned two things. I mentioned myself and I mentioned the person whose finger is touching my forehead. If you remember that, then Newton's third law is an easy one. Let me give you the most screwed up third law example I've ever seen. And it's one that all of you are familiar with. Here's a table, right? On the ground. And somebody puts a box on the table. And the question always comes up, what are the action-reaction pairs for this particular example? And everybody says, oh, that's easy. It's the weight, and it's the normal force, the push of the table, the surface on the box. Well, that's wrong. Okay, that's wrong for this reason. You've chosen one body. You've used Newton's second law to describe what's going on with the box. But if we're going to talk about what's going on for action-reaction pairs here, there are several, but let's just look at the box. What we will say is this. We will say that there is the force of the table on the box. That's one body. And then here's the second body. And we will say that there is the force of the box on the table. Those are action-reaction pairs. And you'll notice I've got two objects that I'm describing. How the table affects the box and how the box affects the table. It's a two-body law. The way to think about action-reaction pairs is that whatever the name of one is, just reverse these two and you have its reaction pair. The force of the table on the box, the force of the box on the table. I mean, you could do this again. You could say the force of the floor on the table, and the reaction pair would be the force of the table on the floor. So you could do this all over the place. But you have to have two things to make it an action-reaction pair. Be very careful with this, because in problem solving, which we'll describe in the next video, sometimes we put things on there to fool you guys. So that is the conceptual aspect of Newton's three laws. Maybe you think you knew this. I hope this helped you to know it better. Okay, that's it for this one.